Okay, welcome back. What we're going to be doing in this video is looking at the idea of adding up actually infinitely many things, which is kind of like a weird idea to think about. And you're probably thinking, well, if you add up infinitely many things, well, that's going to be a, an infinitely large number. And the real answer to this is actually that it sometimes is an infinitely large number, but sometimes it's actually not. And I think the best way of kind of describing the intuition behind this is, let's say that you are standing, um, we'll say 1 foot away from a pizza. Because, I don't know, I like pizza, and I'm kind of hungry right now. Lunch sounds good. We'll say I have a pizza here, okay? I'm 1 foot away from it, okay? Now, in order to get to that pizza, right, I am going to have to walk this whole distance in between myself and the pizza. And I could cut this into a half, right? I will eventually, like after a certain amount of time, I will reach halfway there, right? At which point I will have traveled 1/2 of a foot, right? To get halfway there. Okay? Well, how much do I have left? I still have this other half that's still left over, right? And I could take half of what I had before, okay? Take half of that, and I would get 1/4 of a foot. Eventually, I would have to travel an additional 1/4 of the foot, okay? In other words, what I'm doing here, oops, sorry, this is not quite right. It should be halfway there, okay? What I'm doing is to get all the way to the pizza, I would have to get I would have to half the distance between me and the pizza repeatedly, right? Like I could go 1/2 of a foot, that would half the distance. Then I'm gonna have to reach it so that the distance is half of that, right? So that I cut the remaining distance in half, okay? So I traveled another 1/4 foot. Then I could do the same thing of cutting this piece in half, right? This would give me an additional 1/8 of a foot, right? And I could cut the remaining into another half piece. This would give me 1/16 of a foot that I add on, right? And notice I could keep doing this forever, right? I could keep cutting the distance that I have between me and the pizza in half forever, right? And I would never make it there. I mean, for all practical purposes, I would make it there, but remember, if I just keep halving the distance, there will still be a little bit of distance, no matter how small it is, okay? But essentially what we're saying is, well, what if I look at this as like 1/2 plus 1/4 plus 1/8 plus 1/16 plus and so on, but I don't put an end to this. I don't say like plus some end number. I just say that I'm going to go off for forever. Okay? If I add up these numbers forever, well, we can tell when we add up these numbers, right? We're getting really close to 1 foot, right? That's what we're getting close to. So we would say that the sum here, the series they sometimes call it, converges to 1. Okay, it would be equal to 1 in this case, okay? Because when you are to get anywhere, right, you've got to go you have to half the distance repeatedly, okay? And if you kind of do that infinitely many times, eventually you will get there, okay? So, I know this is kind of a weird idea, but it's kind of cool too. And so what we're going to be doing is looking at infinite sums like this. Like when you have an infinite sum, when will it converge? When will it get close to a number? And when will it just be infinity? Okay. Well, how we kind of write this using our sigma notation. If you remember, our sigma notation meant like when you sum from like I equals 1 to n of a sub I, that means you're plugging in 1 for I, right? Then you plug in 2, and you keep adding up until you get to n, right? This is your stop point. So how we write that with where we're not going to stop is instead of putting an n up there, we write an infinity up there, okay? So that just means I'm doing a1 plus a2 plus, and then dot, dot, dot. I just keep adding up infinitely many numbers, okay? And so, there are some rules that can help us know when something converges. This is the main kind of result that we have when we're dealing with a geometric, okay? When we're dealing with a geometric thing that we're adding up infinitely many times. So how we would write that is the sum from I equals, or I think they use k in the book, k equals 1 to infinity, meaning I'm adding up infinitely many things. And the things I'm going to be adding up are geometric. So I'm adding up terms in a geometric sequence. So my geometric sequence has the equation a times r to the n minus 1, but in this case my variable is just going to be k, okay? So this sum, meaning when I add up infinitely many things that are geometric in nature, okay, this converges or gets really close to a number, okay, and it converges to the number a divided by 1 minus r, okay, if the absolute value of r is less than 1, okay? And otherwise, if the absolute value of r is bigger than 1, okay, the sum will diverge. It will be like infinity, okay? So let's look at some examples here. Find if it converges. Okay. So we've got a sum here. Okay, and notice it's an infinite sum because it doesn't stop over here. Okay, so now what we do is we look at from here to here, right? What is happening to our terms? Am I timesing by something? Well, it looks like between these two terms, I'm timesing by, to go from 2 to 2/5, I times by 1/5, right? And to go from 2/5 to 2/25, again, I'm timesing by 1/5. That will give me the 25 in the bottom, right? Notice the top isn't changing at all. So that's why the top is getting times by 1. And it looks like the bottom each time is just getting times by 5. Okay? So the things we're adding up here have a common ratio of 1/5. That's the R in this problem, okay? So R equals 1/5, okay? So is the absolute value of R, absolute value just meaning you're going to make it positive, is that less than 1? Well, 1/5 is less than 1, so this does converge, okay? And it converges to this number, okay? A divided by 1 minus R. So A is the first term, and then R is 1/5 in this problem. So 2 divided by 1 minus 1/5. So 2 divided by 4/5, so 2 times 5/4. So I think that's going to be 5/2 will be the sum. Okay. So this one converges because the R is less than 1. Okay. The reason why it needs to be less than 1 is that if you kind of remember our sequence for partial sums of the geometric sequence was like this, right? It had A times 1 minus R to the n divided by 1 minus R. And so what we're really doing here is to get an infinite sum, we're letting n be really big, right? And so if R is a small number, if it's like a half or a fifth or some fractional number that's smaller than 1, when you make this number really big, that's going to make this go to 0 essentially, right? When you do 1/2 times itself a large number of times, you would get close to 0, and so you'd get A times 1 over 1 minus R. And so that's where this actually comes from, okay? So let's look at one more example of this. So let's look at another infinite sum here. Let's look at 1 plus 7/5 plus 7/5 squared plus, and then dot, dot, dot. Okay? So you'll notice here, to go from 1 to 7/5, you're timesing by 7/5. To go from 7/5 to 7/5 squared, you're timesing by 7/5, right? So R in this problem is 7/5, okay? So we need to check, is the absolute value of 7/5, well, that just switches it to be positive, which it already was, right? Is that less than 1? Is that less than 1? 7/5 is actually bigger than 1, okay? So this is not true. So the sum, the word for it is diverges, okay? It doesn't converge, it diverges, okay? So you can actually add up infinitely many numbers, which is kind of a cool concept, a very cool concept. So that's it for us learning about geometric sequences. Hopefully this was enjoyable. And we only have one more section of new material before we're done for the year. The last section is 8.6, and it's one of my favorites. From just a math perspective, I really enjoy it. It's not too related to this stuff that we're doing right now. But go ahead and finish up the homework on this. Let me know if you have questions, and I will see you guys in a future video. Have a good one.